Hello, class. Here is your video that supplements some of the topics we've been talking about this week to make up for the time we lost in snow day. I would like to take a moment to reflect on the lessons that were in section 2.3. I know that those concepts can be a little tricky, so I left the last problem of section 2.3 for us to finish up. And I'm just going to hop right into there. So I'm going to share my screen here. All right. Oh, so where did we leave off? Okay, we talked about rounding. Here we are. Okay. So this is the last thing we talked about previously. Let me get my pen ready. All right, so we talked about calculations when they are adding and subtracting versus multiplication and division. And maybe I should just flip back a little bit and just review for multiplication and division. We count the numbers in each number involved and we take the lowest number of significant figures. So in our first example, I just want to go through that one, 36.934, that had five significant figures, 0.11, that has two significant figures. Type it into your calculator. Out of 5 and 2, 2 is smaller, so we round the answer to two significant figures. So in multiplication division, we're counting significant figures. In addition and subtraction, we do something else. Um, One way of visualizing the rule for addition subtraction, instead of counting sig figs, we're counting places after the decimal. So it's two completely different rules. A visualization of this rule for addition subtraction is if you stack them vertically, you can see with our first example, 15.3 and 2.436, we add them together and then we look at the numbers involved. 15.3 only has one place after the decimal, whereas 2.436 has three places after the decimal. We take the smallest of the two so that our answer gets cut off after that first place after the decimal. So we take the fewest number of places after the decimal. So we are going to round to the tenths place, which is one place after the decimal. And we look at the digit after that to tell us if we round, and we don't in this case, so we get 17.7. So I want to combine these rules. We did these. Here's our complicated problem. Now, we were not going to see these in your homework. You're not going to see them on an exam. However, we will see them in lab. So I want to talk about what we do if we have a problem like this one, where I see multiplication and I see subtraction, and how do I handle them when they're in the same problem? You follow the rules of PEMDAS, or order of operation, and you apply the rules as you come across them. You apply them separately, and then you move on. So for example, this problem right here, we have a multiplication, we have subtraction, but the subtraction is in the parentheses, and that is the P in PEMDAS. We always do the parentheses first. So we're going to take this subtraction and we're going to apply the rule for significant figures for subtraction first. So I'm going to enter that. Oh, I didn't bring my calculator. Let me go grab my calculator. Sorry about that. So we're going to enter the subtraction. I'll explain it both ways for subtraction. We subtract 3.492 minus 0.16. 3.492, so subtraction, we look at places after the decimal. That has three places after the decimal. 0.16 only has two places after the decimal. So we are going to round our answer to only two places after the decimal. Some people really like the visual of lining them up vertically, so I want to show you that. So we have 3.49. Oh, this, I thought my little pen was going to be better, but geez Louise, this is not great. I will try to find a better one. Okay, there we go. When you subtract them, you get 3.332. The first number, 3.492. The last digit is 3 places after the decimal. For 0.16, that's only 2 places after the decimal. So my answer has to be cut off after 2 places after the decimal. So this 3.33 that I get, that's going to replace the subtraction. And now I'm going to multiply that 3 by 3.33. So I've rounded 4 significant figures using the subtraction rule. Now I'm going to do my multiplication, ignoring the numbers that were in the subtraction. They're now replaced by 3.33. I multiply that by 5.2200. And now I apply my rule for multiplication, which is number of overall significant figures. So my rule for overall sig figs, and let me change my pen color here, 5.2200, this has 5 significant figures. All right, because when I add zeros at the end of a number, if there's a decimal present, they do count. I'm adding precision. 3.33 has 3 significant figures. So when I multiply these together, and I get 17.3826. I apologize for my writing on this. I'm only allowed 3 significant figures, so I'm going to look at the 17.3. The 8 rounds the 3 up, and so my result is 17.4. So keeping track of which rule you're dealing with is everything in section 2.3. If you are dealing with multiplication division, you're counting sig figs. If you're looking at addition subtraction, you're counting places after the decimal. Okay, so we are going to continue on, but that's really the crux of section 2.3 homework. When it comes to the homework for this section, don't be too concerned about showing me work. You do not need to show me work for this section. I know that a lot of people can do the sig figs with calculations in their head, and that's okay with me. Okay, I want to move on to section 2.4. So 2.4 is taking a look at the metric system. So the metric system uses a series of base units. For every type of measurement, there's a base unit. So examples are meter, second, liter, and gram. A meter measures length, a second measures time, liter is volume, and gram is mass. Now let's say we take the meter. So the meter is about the length of a yard. If I'm measuring the length of, let's say, a paper clip, that's pretty small, right? Using a unit that's much, much bigger than the object I'm measuring doesn't make much sense. So I'm going to want a much smaller unit. I can make the unit smaller by adding a prefix. And so the metric system has many different prefixes. So here's examples. Kilo, if I add kilo to meter, kilometer, or kilometer, that makes the meter 1,000 times bigger. And whenever I see kilo, it's making the unit 1,000 times bigger. Millimeter. Milli is making it 1,000 times smaller. Centimeter is making the unit 100 times smaller. So these prefixes we add to the base unit and it changes the size of the unit. The prefixes that we will be seeing in this class are on this chart. This chart is at the top left corner. If you look at your purple handout from class, the front side is the periodic table and the back side is, oh, I realize I haven't given you guys your purple sheets yet. You will get your purple sheet in class and we'll look at this together. So this table will be on a handout that is given to you with every single quiz and the final exam. So you do not have to memorize this chart, but you do need to know how to use it. So you're going to get a reference sheet. It's the purple reference sheet. I'll hand it out in class on Monday. And how we use this table is that as we go up the chart, the units are getting bigger. So these are the biggest ones at the very top. And as we go down, these are the smallest prefixes. You'll see that the base units are right in the middle. And as we go up, the units, the prefixes make the unit bigger. As we go down, the prefixes make the unit go smaller. The power of 10 that's defined to the right of the prefix, that is telling us how much bigger or smaller the unit gets when we attach the prefix to the base unit. There's a couple notes here. So each of the base units has a one-letter symbol. Liters is L, meters is M. When I add a prefix, I'm adding a letter to the beginning of the symbol. So we are talking about kilometer. Kilo is a K. Meter is an M, so the symbol for kilometer is KM. I want to talk about the symbols for a few of the prefixes. I want you to look at milli and mega. Do you see how they are very similar? Mega is a capital M, an uppercase M, and milli is a lowercase m. In addition, meters are a lowercase m. So millimeters looks like two little m's, but megameters is a big M and a little m. So right now, get your handwriting straightened out so that I can tell your uppercase letters from your lowercase letters, and so can you. Because the difference between a lowercase m and an uppercase m can make a huge difference in writing units. It's also going to make a huge difference when we get to talking about chemical symbols for the different elements. So it doesn't have to look exactly like my handwriting, but it does have to differentiate in some way between uppercase and lowercase letters. Another note I want to make is micro. This symbol right here, this is a Greek letter called mu. It's like a U with a little tail. I like to write it like a straight up line and then a little U after it. So that's micro. How we use this chart, so we're going to be using this chart to write equations. Oh, before we start, I want you to look and tell me which of these units is the smallest measurement. So take a moment. Which one's the smallest? I'll take a sip. If you said microgram, you were correct because microgram is the furthest down the chart. This is helpful for us because knowing if we're comparing two units, which one's bigger, that's going to be very important for writing an equation to relate two units to each other. And that's the next skill we're going to work on. So when we are interpreting prefixes and writing an equality between a base unit and a unit with a prefix, and this is the only type of equation we're going to learn how to write from this chart. What you're going to do is you're going to set up an equality with blanks before the units. Let's do one together. So let's say I want to relate nanometer and meter. So my base unit is the meter. The unit with the prefix is nano here. You can only write equations when you have a base unit and only one prefix. I'm going to show you why that is in just a little bit. So we write the equation, then we write a 1 in front of the bigger unit. So we look at the chart and see which one is higher up. The meter is higher up, so that gets the 1. And then we look at the prefix in the equation. There's only one prefix. It may have the 1, it may have the blank. It depends on if the prefix makes the unit bigger or smaller. But we're only allowed one prefix per equation because that prefix tells us what's going to go in the other blank. So we look at nano, and I'll go back and we see that nano is 10 to the negative ninth. That is going to go in the other blank. However, we always make the power of 10 positive if it was negative. If it starts out positive, we keep it positive. So since nanometer is 10 to the negative ninth, we make it 10 to the positive 9. I like to tell people to remember that because we make our powers of 10 positive because we're positive people. I often get asked, why do we make it positive? Well, when we put the 1 in front of the bigger unit, that means we need a whole lot of the little units to fit into the same size as the big unit. And so when you have a power of 10 that's positive, that means we have a whole lot of that unit. So we want a lot of the little unit. Let me show you another example. So let's say, I want to make sure I'm not repeating anything. So we were doing kilometer. Let's do kilometer and meter. And I could write this in the opposite way. I could do meter and equals kilometers. It doesn't matter. I put the 1 in front of the bigger unit. So I see that kilo is above the base unit meter. So I put the 1 with kilo. But the kilo that is what tells me what goes in the other blank. So I look and I see kilo means 10 to the third. It starts off positive, so I keep it positive. 1 kilometer equals 10 to the third meters. I'd like you to take a moment, stop the video, and just practice these ones by yourself. Okay, did you actually stop it? I hope you did. And practice these because practicing it on your own, even if you don't get it right the first time, it's getting your mind to think the correct way eventually as you correct your mistakes. So I'm going to go through all of them. A is micrometer and meter. Meter is bigger, so I put a 1 there. I look at the power of 10 for micro, and I see that that is, if I go back, micro is 10 to the negative 6. So I make that 10 to the positive 6 because I'm a positive person. 10 to the 6th. Ooh. You will see that your book often writes it as 1 times 10 to the 6th. That means the same thing as 10 to the 6th. I'm okay with either way of writing it. Okay, let's try the next one. Deciliter and liter. 1 liter, the liter is bigger, so I give it the 1. Deci is 10 to the negative 1. I make it positive. That is 10 to the first. Now that is equivalent to just 10. So if you wrote 10 or 10 to the first, either one's okay. Our last one is megasecond and second. Mega is bigger, so that gets the 1. The power of 10 for mega is 10 to the 6th. That goes in the other blank. We will practice this just a little bit at the beginning of class. Let me know if you have any questions on this. And we're going to continue on. But this will be in the homework for section, I think we're in 2.4. Yes, this is section 2.4. Now, one thing about units, and there's a special little caveat with our volume units that you should be aware of. Units of volume, there's 2 different types of metric units for volume. The base unit for volume is liter, and that is defined as a 3-dimensional unit. We can also create 3-dimensional units by looking at if I had a cube and every side was 1 centimeter. All right. So every side was 1 centimeter. I have a 1 centimeter cube. If I were to find the volume of that, that would be equal to 1 centimeter times 1 centimeter times 1 centimeter. We did that in lab, right? And our unit that we ended up with was cubic centimeters. That is also a metric unit of volume. The relationship to relate the liter-based units and the cubic volume units is actually really nice. 1 milliliter is exactly the same in volume as a cubic centimeter. And cubic centimeter is abbreviated in the healthcare industry as cc. So if you see 1 milliliter, 1 centimeter cubed, or 1 cc, they are all the exact same unit. And that's going to come in handy in lab next week when we see milliliter and centimeter cubed included in our density units that we'll be learning about. So that concludes section 2.4. I would like to start section 2.5 as well, because section 2.5, that starts to talk about, well, what about when we compare metric units with English units? I do not expect you to memorize any of the equalities involving the English or the US unit. So English was the old way we would call it. These are the US units. All right. Your book has a table to relate all of these units to each other. You do not need to memorize them. It is table 2.8. And I will have some of these listed on your reference sheet on the back of your periodic table as well. But some examples, if we're relating inches and centimeters, there's this equation. I have the equation for liters and quarts, kilograms and pounds. You do not have to memorize these, and you will be using these in your homework, but you can get them from the table. Let me get the book so I can tell you exactly what page. Oh, I forgot it's right here. My laptop I set on top of my book. So this table 2.8, this is on page 43. 43, page 43. That gives you a listing of a whole bunch of US to metric conversions. You do not need to memorize them. But what we're going to do is we're going to learn how to use them. So the equalities between metric units, we're going to learn how to use those. The equalities between US and metric units, we're going to learn how to use those. And when we have an equality, it's really important for us to be able to translate that into something called a conversion factor. A conversion factor is a fraction where the top of the fraction and the bottom of the fraction have equivalent values. These are the key to unit conversions in chemistry. In this section, we are going to practice how to take an equality or a ratio and write it as a fraction. It is fairly simple. However, getting this down is a huge step in progress to getting to the unit conversions we're going to be doing in section 2.6. And those can be challenging for a lot of students. And one way that I like to break that down is really concentrating on how to write something as a fraction, because that can simplify the thought process. So whenever you have an equality, you can write it as a ratio or as two conversion factors, which are two fractions where the top and the bottom are equivalent. So if I have the equality 2.54 centimeters equals 1 inch, I can look that up in my table 2.8 in the book. I can always write any equality by replacing the equal sign with the word per. So the ratio 2.54 centimeters per 1 inch means exactly the same thing as my equality. And then I can write that equality or that ratio as two fractions by taking what's on one side of the equation, the 2.54 centimeters, putting that on the top of the equation, putting what's on the top of the fraction, taking the other side of the equation, the 1 inch, I put that on the bottom of the equation. So now the top and the bottom of my fraction those are equivalent. That is key to doing a conversion. I can also flip my equation. If I were to flip my centimeters and my inches, what I get is my second fraction, 1 inch over 2.54 centimeters. Those are the two conversion factors for this equality. In section 2.5, you are going to practice taking an equality or a ratio and writing it as two conversion factors. Let me give you another example. If I were to tell you that we were traveling in a car at 42 miles per hour, we could write that as an equality. What that means is in 1 hour, I will have traveled 42 miles. So I could write that as the equality 42 miles equals 1 hour. And then I can write that as two conversion factors by writing, and I believe in these fractions, I am using the abbreviation for mile an hour. I can put 42 miles over 1 hour, and then the other fraction, I just flip those two, and they're both conversion factors. So the key to writing a conversion factor is making sure that the top is equivalent to the bottom. And it does not matter which one you write first. If I wrote 1 hour over 42 miles first, that's fine. We are going to learn which one will be appropriate in which situations. So what I'd like you to do is take a look at problem example 5. And this may make you sweat a little bit, is a word problem. We're not going to do the word problem. But in chemistry, I'm going to teach you how to take a word problem, break it apart so that you know, I'm going to give you a way to approach word problems. This is something that I found magical about chemistry because I hated word problems. I was like, I don't know where to start. You're just throwing a bunch of numbers at me. Chemists, we have a very methodical approach to things like word problems. So you can think like a chemist, even if you're doing something that's not chemistry related. So in this case, I have this problem and it says to become a professional court reporter, you must be able to type at least 250 words per minute. That is insane, by the way. Super fast. At this rate, how long would it take a reporter to type a 4,000 word essay? We're not going to calculate that, but we're going to learn how to start to approach this problem. And the first thing that I want you to be able to do when you're given a problem like this is I want you to find any ratios. We're just hunting for ratios, all right? And the word that means ratio that should send like alarm bells in your head is per. So have you found the ratio yet? Underline the ratio. You should have underlined 250 words per minute. We are going to be doing this for the rest of the semester. We're going to have a whole lot of word problems, and the first thing we're going to do every single time is find the ratios because those help us decide where our starting point is. And whenever we see a ratio, we're going to write it as a fraction. So I want you to write this as two conversion factors. How we do that, everything that comes before the per, so the 250 words, that goes on the top. Everything after the per goes on the bottom with a 1 per minute. That means per 1 minute. So my fractions are 250 words over 1 minute. And then to get my second fraction, I'm just going to flip it. 1 minute over 250 words. So we're going to practice this more in class on Monday, but this is just a good start to writing those fractions because that's going to be absolutely key to what we're doing all next week. So our next week, which is the first week of February, that's going to be absolutely key to doing our calculations. All right, so I'm going to stop my share there. And I hope this video wasn't too taxing, and I thank you very much for watching it over the weekend because it's going to help us keep on track with our lessons in Chem 100. Stay warm, everyone. I will see you on Monday.